So I consult the wisdom of the ages on the Google machine, and what comes out, interestingly, is what's called a featured snippet. And a featured snippet is a thing that comes on because now it's too boring and slow to even click on a link on Google. So they have 16 million results, but that's just too slow for us now. So we need, and I looked into the definition of this, we need accurate and fast information. And so they look through all these pages and they pull out the relevant information. And as a side note, I can say, by the way, I studied this. I'm not going to talk about this at all. I'm just showing off. I studied this, and this is part of a process that's actually happening, and we show it in many different systems, that everything is going faster. Everything is moving faster, and this is just one symptom. But in this reliable and accurate piece of information, the featured snippet, something very interesting happened. I looked at it, and it turns out that apparently inaugural lectures must be held in Dutch. So, of course, welkom bin met Choratje. Yes, thank you. I promised bad jokes, and it's just gonna be an hour of this. No, actually, I thought this was a good occasion to answer a question that a lot of times and this is genuine, I have difficulty answering myself, which is, what is it that you do? People say, well, what are you working on? And I draw a blank. I say, well, I type keys on a keyboard. I know that. But now I had a chance to kind of look back and reflect. And I think a good way to break it down is to look at this title. And we can kind of move it around. And already this idea of being professor of complexity just sounds silly, right? My students immediately started to make fun of me. They were like, Mr. Complexity now? Is this happening? And I think the way to read it in a way is that you should put in science, both places. So it's complexity science and network science. It makes more sense, but still, what is complexity science? It's also not very well defined. And I had the presenter view on, but now I have no idea what the next slide is going to be. But I guess to really understand what complexity science is, you have to understand the context, and you have to understand relationships. And the specific relationship that we have to understand in this case is the relationship between DTU and the messiness of human beings, the thing that people study in the social sciences. But at DTU, you can't really be a professor of social sciences. We'd be impinging on the social sciences and so on. So I think, in a way, complexity is a way of defining a relationship that's complicated. Or, to put it differently, it's complexity. So let me talk first about some of the work I did in complexity science. And this first part is going to be a little bit like a list. It's going to be the most boring part of the talk. But to open it up, I'm going to not talk about the work I did on Twitter, because I'm actually going to now leave the stage for a moment and present some science communication done by a little outfit called the CBS Evening News. This is from 10 years ago, about the work that we did then on Twitter. And this is, I believe this is the first study anyone ever did on Twitter. And you can see it's a little bit dated. Look at the cell phones and also the explanation of Twitter. But let's try it now.
This is your country. This is your country on Twitter, a minute-by-minute, color-coded, pulsating chronicle of the country's mood, based on words used in tweets, those quick electronic messages. Red states are mad, the tan and green states are happy. We feel pretty good early in the day, get mad later, and happy again before bedtime. How many tweets did you study?
About 300 million.
300 million?
That's actually a very small number.
Oh. Lehmann programmed his computers to look for hundreds of happy words or sad words in tweets. Words like diamond, love, and paradise were considered happy. Funeral, rape, and suicide, not so happy. We use the happiest words on Sundays and get sadder as the week rolls on. Tell me, where are we the happiest? Where are we the saddest?
So I can tell you that the happiest state consistently is Hawaii.
Well, that's not, you don't need 300 million tweets to tell you that. In fact, most of the western U.S. is apparently happy.
A little sun might do that to you. Little sun, walking on the beach.
I'm in New York. How happy should I be?
I would say the whole East Coast seems pretty grumpy.
You're breaking my heart. I was in a pretty good mood till you told me that.
Yeah, but that's how it goes.
Truth is, in New York, it wasn't hard to find grumpy people.
If you get in the way of what we want, we let you know it.
So is this science? Can you really gauge the mood of a nation by tweets? Maybe not yet, but Lehmann hopes soon we will.
I think potentially this could be a very valuable tool.
Encouraging news on the most discouraging day. According to Lehmann's calculations, the grumpiest time of the week is right now, Thursday evening. So how do you feel? I'm fine. I thought. Richard Schlesinger, CBS News, New York.
Yes, I saw it and it was too good not to include. It turns out, so I've been looking back, and it's been a lot of fun, that I've been a trailblazer also in another area of Twitter. So back in 2013, I was teaching a class, one of my award-winning classes, as Yen mentioned. I say so very humbly, of course. I decided that it would be fun. They were learning about networks and they were learning about text analysis to build little bots on Twitter. This was not a thing at all at that point, and see if we could somehow interact with the people out there. And that turned out to be a wild success. Our bots could agglomerate followers very quickly, so they looked like real profiles and they had thousands of followers. And we decided to see, could we somehow make an impact on Twitter? So we thought, can we somehow influence the trending topics on Twitter? And again, to make a very long story very short, we actually succeeded. Okay, and we spread a rumor that the artist Banksy was in Boston, and people believed it, and it started trending. And we had a lot of fun. This is also, now this talk is being filmed, probably is not the right research ethics. But anyway, we did it. And we wrote about it. I wrote about it in this blog post. And what we said, and I think it's fun, is that we said we did show that a few dedicated bots can make a difference. And we also said, this is in 2013, where there were no bots. And we said, could use a network of sleeper bots to systematically spread misinformation, injecting talking points into Twitter streams on a global scale. And I had forgotten all about this, but in preparing for this, I went back and read it, and I felt like it's pretty good. At least there were some Russian guys who read this and and went with it, yes. So this is some of the work I did on Twitter. Now comes the most boring part of the talk. I realize I should have cut it, but I just couldn't. I want to just show a little bit of why it's called complexity, what I do, because it is a lot of different things. I talked about the Twitter. We also wrote papers about that. Some of the work I did, some of the most recognized work, in fact, has to do with scientific citations, right? We write papers. They cite each other. It forms a network, so I've done a lot of work on that. A few years ago, we did this thing where we wanted to really collect a really good network data set along with collaborators at the University of Copenhagen. We found funding to buy 1,000 phones. You can see them here. It's a lot of them. We put custom software on all of them, and we used the phones to measure the networks between all the freshman students at DTU, who is close to whom. The phones can see that through Bluetooth, but also who calls whom, who emails whom, and so on. And when I started doing that, that's when it really got complex in a way. All of a sudden, we hadn't thought about this, but we did a lot of work on smartphone sensors. phones don't tell us about social networks. They tell us about little annoying JSON packets, and you have to interpret them. We also did a lot of work trying to understand how diseases spread, because all of a sudden we had this incredible network of how people actually meet in the real world, and we could study and simulate how diseases spread. The phones also have GPS, so of course we could also study the patterns of how humans move around. This is something we're still very actively doing. We had some very nice publications last year, and we're working on something now that I'm also very excited about, but we're just going to skip it, of course. We also did a lot of work on privacy. When you're more invasive than Facebook in terms of studying what people are doing, then you have to figure out how to do it in the right way, in a way that protects the people that are involved. And I realized it would get boring to look at all these flying paper cover pages, so we also studied academic performance. We also study sleep, because people check their phone typically before they go to bed. And when they wake up again, how does this impact networks? We're now also studying how do people use apps? Why do we become addicted to our phones? We use large data sets to try and understand how does climate change impact human behavior. And we also do a lot of other things. So it's just to say it is quite broad. Okay, so this is a list. I need it for my own sake to get through it. I'm sorry. But now I'm going to try and actually tell you about some of the science. All right, the network stuff, in a way, it's less flashy and fun than the Twitter, but it's what I think is more appreciated by scientists, other scientists. So when we think about networks, what I mean is simply that we can imagine representing many different systems in a very simple way, just by dots, the nodes, the actors in them. That in a social network, that would be people, and then links, which would be the connections between them. And when we get data from real networks, what we find is that at every level, it's more complicated, complex, than you would anticipate. When we look at characteristics of single nodes, they're completely different than you would see if the network was random. Similarly, if we look at motifs of a few nodes that are connected, some are suppressed and never occur, even though they should. If things were randomly wired up, some occur much more. And this shows something about what's important locally in that network. If we look at slightly bigger things, modules, groups, in social networks, it's easy to understand that humans form groups of friends or soccer teams or families and so on. So the network is more interconnected there than it is to the rest of the network. And typically all of this is organized somehow in a hierarchical structure. So what does that mean? It means that at universities there is departments and DTU sections, and within the sections there are research groups and so on. So there is this hierarchy. You're more likely to be friends with someone you live nearby than someone you live far away from, and so on and so on. So there's all this structure. And what we're going to talk about today is what we call communities. This is this tendency of the network to clump together. All right? Now, the way to think about communities traditionally in the field is to say, well, we have these nodes, these groups, they're highly connected between each other, and they're weakly connected among each other. And if we look at pictures like this, we see that they occur all different places. And I also want to say, just so you understand, this is like something people really love to do. So it's like a super popular topic. I tried to quantify at one point how many papers came out every year, and it's something that scientists write literally many thousands of papers about communities every year. And in this paper from 2004, this group of Italian gentlemen decided to try and sort of say, let's get all of this different definitions up and just make the most straightforward definition of how you would define a community. And they put up two equations, but the intention of it is kind of easy to understand. They say there's a strong sense of a community, which says that all the nodes in this grouping must have more links pointing inwards into the group than out to the rest of the community. And then there's a weak sense where we say, well, maybe some nodes can point out a little bit more, if that makes sense, but the sum of all the degrees pointing inwards is better, right? So this makes sense. This is sort of the baseline of this must be true for communities, one would think. But in 2010, when I was a postdoc in Boston, Jim Bagro and Young-Yol Ahn and I began to think about this problem, and we thought, is this really the right way to think about groups in networks? It seems so straightforward. Thousands of papers are being written in this direction, but when I look at my own network, and this, so I'm digging out the old, stuff here. So this is what my LinkedIn looked like in 2011, and you can basically see that there's me in the middle, and I connect some groups. And one group is the people that I work with in the U.S. Another group is the DTU guys. Then maybe the people that I'd lived in a dorm with, and people I went to high school with, or whatever. But you see that there are these different communities, and I'm stuck there right in the middle. So if we make a cartoon of this, it looks like this, right? That represents how human beings participate in networks. We have an ego in the middle, and then we have, let's say, the family, the soccer team, the group of friends, and the people from work. But if you think about this, what does the whole network look like? And essentially, what happens is that if the local structure around a single node looks like A, the whole network becomes a hairball. It doesn't become this beautifully clumpy thing. Okay? So we made this point that actually real networks aren't going to look like they did in those thousands of papers people were publishing. You could just kind of reason, we plotted another way of thinking about it is that here we take two nodes and we kind of show that if they participate in all these different communities, the whole network is going to be one big hairball. It's not going to have this nice structure that we see in all the drawings. And this is not just something I'm making up, and I'll show you other examples of this, but this is a real network. And what I'm going to argue is that this network has lots of structure of exactly the type that I was mentioning before. So it means not only, and I think this is really interesting, we have to throw away this picture, but even more crazily, we have this common sense definition we also have to throw away. Because if I'm a member of more than one community, that means that I have many more outgoing links than I have pointing to each of the communities that I participate in. So this thing that seemed so clear and so common sense actually isn't so clear, and it doesn't make so much sense. Okay, so now we've said everything is wrong, but it's also nice if you try and do something constructive. So what we pointed out was that even in the case where nodes in the network belong to many communities, the links, the connections can be categorized. So in some sense, the links between members of a family are similar to other links between members of a family. The links between the soccer players are similar to each other. And so on. And so we can cluster the links without this overlap. And remember that in this picture over here on the right, you can see that the node in the middle is just one example, but every node is like that. Every node is split up. So based on this idea, we developed an algorithm. And this network is the network of word associations, so similarities between words as perceived by people. And what we find is communities that look like this. So if we take the word brush, we see that we basically can extract the different connotations. We can see the word brush as in sweeping and broom. We can see the word brush as in paintbrush and painting. We can see the word brush as connected to toothbrush. And we can see the name brush in connection to grooming hair, right? And it doesn't make sense to say that all of this should be one community. It really needs to be fundamentally overlapping. So this is the paper that we read. I'm just going to take a break because I can't remember like what's coming up, and my talk will be way better. So I'm just going to reformat the screen so that I know what the next slide will be. So in case there's some jokes coming up or something, I won't spoil them. Is that okay? It's good. It's going to take 1 second. Okay, here we go. Yes, so this is a paper we wrote. It came out in a very fancy journal, and it was kind of a very nice moment. And so when we had published this, I thought, okay, you know that in Japan they developed this business strategy. Actually, I don't know if it's Japan. I'm just making this up. There is a business strategy. I think it's called like the blue water strategy, something like this, right? And it says something that if you're a corporation, you shouldn't be where all the sharks are fighting for all the same fish. You should head out on the, it's probably called blue ocean. You should head out on the blue ocean where you can just go nuts and eat the fish out there, right? So community detection, thousands of papers. Sune was thinking, now I'm talking about myself in the third person, this is terrible. I was thinking, I need to get out into the blue ocean. I can't be in this place where all these people are just writing papers and papers and papers. So I felt like we made a good contribution to the field, and now I wanted to do something completely different. And so that's what drove this whole move over to cell phones, right? So by some miracle, I said, this is the new technology. We need better data to really understand networks. At first, I was just sitting around grumpy that no one was collecting a perfect data set for me. But then I realized maybe I should just do it. I had just arrived in Denmark. I needed to apply for some money, and this seemed like I didn't know what else to spend money on. I just wanted a new laptop. That wasn't enough, so this was like a great idea. So we went out, and we got these phones with the purpose of saying, we're going to collect the most amazing network data in the known universe, and by having this data, we will discover completely new things. That was the idea. I said something different to the people funding me. I said we do have some plans, but honestly, between us here, what I wanted was just an incredible data set, and I was sure something amazing would come out of it. And the experimental design, the thing that's really important here is that what we did, other people had handed out phones also, but they had never managed to cover a whole population. They had never managed to cover a group of people with lots of social interactions between them. Okay, they had only sort of said, well, I know one guy who will do this, and I know another guy who will do this, and there's also someone over here. And so they got phone data from people, but they never got information about social systems. So what we wanted, and the green blob here is real data, and it represents the proximity context, so the people who were close to each other at DTU for one day. So what we got is we got this network that had unbelievably related, compared to the literature, high density of social interactions. And this, and I don't have time to go into all the different things we collected. We collected the like I said, the phone calls and the text messages, who was close to each other, the GPS. We also collected personality tests, all these things. And this is an unbelievably rich data set. So here's a video where each person, or each blue dot is a person, and we connect the blue dots with lines if they're close by. And then you can see the DTU campus where you're at, and you can see people moving around. They're going to lunch right near where we are now. Now they're leaving again, I guess. And so you can see these blue dots moving around. And just to give you a sense of the data set, this is not a simulation, right? This is not, you've seen maybe simulating data like this, but each dot is really a person. It's some young man or woman with hopes and dreams, and they're going somewhere, they're thinking about homework and classes and what they have to go shopping. They are exhibiting this exactly unpredictable, crazy behavior that we see students exhibit, at least to some extent. Actually, they're pretty predictable, but that's another story. But it's a crazy data set, and this is just one data channel. This is just a GPS, but we have all the electromagnetic spectrum that they're seeing, the Wi-Fi routers that their phones connect to, the cell towers, on top of all this rich network data. So now we have the data. What are we going to be working on? And so what happened was that we're looking at this hairball, and we realized something quite interesting, which is this is what one day looks like. this is what 1 hour looks like. And when we look at the Bluetooth connections that we record just within 5 minutes, something kind of incredible happens, and you should be prepared to experience it because you already know about communities. The network falls apart. We hadn't anticipated this, but on second thought, it kind of makes sense. Each little group of nodes is just people that are separated from each other in space, right? So there's 5 people over here, 2 people over there, 10 people over there. And if they're close to each other, the Bluetooth sensor is going to ping, and you're going to see a densely connected group. And if they're far away from each other, they're not going to see each other. But this is kind of incredible, because I just told you that there's a whole field dedicated to finding these structures using very complicated math. But here, basically, just by getting a better data set, just by capturing the system at the right time scale, the communities just come out completely naturally without us having to do anything. And let me say, usually more data, more temporal resolution means much longer and much bigger and much more scary equations. So we had this, and we realized we have not just one time slice, but we have a huge number. So we can match these groups up from time slice to time slice, and we call this kind of meetings of people for gatherings. All right, so this is a group of some people that meet at some place, and then they hang out for some amount of time, and we can find them in each time slice and then match them up. And so the picture that comes out, I made a little movie here, you can see the network view over on the right. Over on the left, you see the day from morning to evening, and you see a line moving down that's time moving from morning to evening. And then each group is one of these, we call them sausages. So one of these sausages in time is a group of people, and the width corresponds to how many people are in the group, right? And then you can see the network over there on the right. So this is what meetings look like, and it's unparalleled in a way. We can immediately calculate what are the statistics of the duration of meetings. Does the fact that there's a lot of people influence how long they are? We can calculate all these cool statistics. And this is already kind of revolutionizing and should make us feel good about collecting all the data. But even more so, we found that if we have people that are truly friends and not just meeting randomly at some point, they're going to meet again and again, right? So we have the gatherings, which is how one meeting works. But actually, the group of people would also meet again and again. If they're friends, they're going to see each other again. So we can also do another level of matching where we actually find how people line up over much longer periods of times of days and weeks and months and how the meetings recur. All right? And so what this does is it dramatically simplifies the whole network. Instead of thinking about these millions of nodes that are coming at you, the activity of changes, we can move to this view of jumping from social context to social context to social context. So we all of a sudden reduce the complexity, yes, I said it, of the network dramatically. All of a sudden it becomes much simpler. And so here, for example, we plot just one person, the groups that they're in, and then how they participate in those groups over time, right? And so I'm not, like, details now get a little bit more boring. This is sort of the general idea. But we can use this to, for example, predict what people are going to be doing in the future. We can use this for all kinds of really interesting applications. And we wrote also another nice paper about this, which was good because that meant that I could now justify that they had given me all that money to collect the data to go fishing for new ideas, because I was a little bit worried that I wouldn't come up with anything. And what was even more fantastic is that there are deep connections to the work I did back in 2010. So I had tried to do something dramatically new and different, but it turns out I dug out this illustration, and I realized that we had just been doing the same thing one more time from a different perspective. So I guess the lesson from that is that it's impossible to get any new ideas ever. Thank you. No, no. But anyway, so this is where we were in 2016. I was feeling great about myself. This is right when I heard that the paper was published. It's a true photo. And I thought, this is going so well. I invented this amazing algorithm, and now we're just going to apply it to networks everywhere, and I will be the king of science forever. And so we took the algorithm and we said, let's try it out on some Facebook data, right? We have all these different data sets. We have the phone calls, I didn't say, but we also collected the Facebook friendships. And so we said, well, let's plot these beautiful snapshots of Facebook data. We did, and they didn't look like we wanted them to look. They looked totally different. And if we aggregated, they also looked totally different. And when we tried to look at this temporal inference of the communities, nothing made sense. And when I tried to do this beautiful sausage plot that we had discovered and celebrated, they also looked completely wrong. So something was going on where that we couldn't apply this to Facebook, right? And just to compare and contrast the beauty of it, here is this mess that comes out when you apply this algorithm to Facebook, and this is what happens in the Bluetooth network. So all this sort of clean, beautiful mathematical description all of a sudden had disappeared. So what's going on? Normally, when I talk about this, I now turn this question out to the audience just to make you wake up. But I think maybe today is not the day for it. I'll just reveal the answer. Basically, what's going on is that the networks are completely different on this microscopic level. So the key is still the microscopic level, but the networks are different. We can illustrate that by something that we all know about, the phone network, for example, right? So we agreed that the face-to-face network showed this clumps of people hanging together. But if we think about what phone calls look like if you make a thin time slice, you would just see people talking on the phone. So the fundamental thing that's expressed there in the thin time slices is just pairs of people engaged in conversation. And so the whole network disappears in a way, and it only arises when you aggregate over time. See, that's why I need the presenter view here. So the problem is that the networks are totally different from one another on the microscopic scale. And if we want to generalize even more, what we really have to think about, and I think this is so important when we think about data that comes from technology or anywhere, essentially, is that the generating process itself, the technology that we build to record what's happening, imposes constraints on what we see. All right? So in the phone network, you can only have dyads. I mean, I know that they're conference called, but I choose to ignore them. Here, it's not so important. So you may say, since you're sitting here, and say, well, this is obvious. Of course it's like this. Why hasn't anyone made this point yet? And the point is because no one had the data to force them to think about it. I had to take my algorithm, apply it to Facebook, see that it didn't work, to even get this idea of that there was something wrong. And so this is another payoff from collecting all that data, is that I was actually the only person who had the data to see this, because we had the face-to-face meetings, we had the Facebook connections, and we had the phone calls. And when you aggregate them, they look similar. When you look at a long period of time, you see the same thing because they reflect the same underlying reality of people that are friends with each other, and they're expressing their friendships through all these different channels. And so once you realize this, you can think, well, is there something more general going on? I think there is. If you look at communication studies, for example, they like to separate the world into 6 categories. These might not be all of the possible categories, but I think they're interesting ones. You can think of one-to-one communication, like emails or text messages or talking to someone. You can think about one-to-many communication if you write a web page and a lot of people read it, or old-fashioned broadcast radio and television. And you can think of these many-to-many connections, like the cliques we looked at in the first issue, right? And the cool thing is that there is an associated network footprint of each of these types. There's another important split, which is synchronous and asynchronous. Synchronous just means we have to all be here and be engaged for the communication to happen. And then something like an old-fashioned letter, that's asynchronous. You write it, you put it in the mailbox. Now with PostNord, you have to then wait 3 to 4 weeks, and it arrives just down the street. But much later, someone engages with it. Same thing with text messages or whatever. So this is another important split. And the phone network is a one-to-one synchronous network. The face-to-face network is a one-to-many synchronous network. And like I said, the cool thing is that each type of communication, we can kind of map it to somewhere in this matrix. And as I said before, this has key and very important consequences whenever we model and compare networks. And so what I did when I thought I solved the universe and everything in the paper with the Bluetooth interactions is that we just solved this one corner of this matrix. But in fact, we need to develop theory and different theories for how to treat networks in each of the corners of this matrix. And I'm not going to bore you with how we should do this. This is something I'm just thinking about now. I just wrote one little paper about it, but I think there are some really important things, and just one key example I want to pull up, which is when you study spreading processes on networks, so like things where someone is sick, they cough, and then they might infect some other people, and it spreads on the network. I talked about us working on that. They're finding this thing that if people have empirical data, sometimes the network and the fact that you have temporal data and not just simulating on the static network makes everything spread much slower. And there's a whole stream of literature over to the right, I guess. This is very difficult with the directions. Over to the right that says everything slows down. And there's another literature that says, no, actually, when you have the temporality, everything goes faster. And this has been, in a way, a riddle. And people have been arguing, saying, why is this the case? And I think that it's because that the fundamental structure, the way that interactions are expressed in these temporal networks is different. And some types of structures makes things slower, other types makes them faster. There's many more examples. All right, but if you're interested, you can read about them. I wrote a little note. It's just being published. But this is kind of the whole path, taking you all the way back from 2010 up to like the most recent things I've been thinking about networks. You can see that this document, I made it in July of this year. So this is the network science part. All right, we're close to being done. Already. It's so great. I was worried I'd go way over time. I have something like 900 slides, but I went through them very quickly. So now we're going in, and now I'm going to be super serious now. I want to make some acknowledgments. No one goes from being, this is me, first day of school, back in many years ago. No one goes from being that little boy to being this old, boring man without lots of help from lots of people, all different places. And actually, I said I wouldn't do any more jokes, but I want to flag up one thing, which is I was already super silly even back then, which I'm proud of. But yeah, I want to say thanks to some people. And as you can see, I've been looking back and putting this talk together. So in looking back, I also looked at my own PhD thesis. And it turned out I'd written pretty great acknowledgments back then. It's always good when you can look back and be like, this wasn't as terrible as I remembered it. So I want to go over those acknowledgments and then expand them just a little bit. So I want to say that there are some people that have been incredibly helpful through the years. Andy Jackson and Benny Lautrup worked with me during my PhD thesis. They were incredible, and they really helped me learn how to be a great scientist. I've met with them both recently, and turns out they have felt the same way, which was nice. They also felt that we had something special going when we developed some of the work we did then. So that was really a relationship in the old school of learning science. You meet with some old, experienced people, and they teach you how to think about the work and how they think about the work, and it was pretty great. Of course, also the best boss in the world, Lars Kai. I can't say enough how thankful I am to the way that you do things and making every day great by giving freedom and being also awesome and smart and having the right advice almost always. Thank you so much. It's not always, but it's pretty close. This is the part that needs to be amended a little bit. There's many other teachers and mentors, too many to mention, but that's been great. Collaborators, students and postdocs are the best. They really are. They make fun of me. They're smarter than me. They do all the work. I just sit and type on the keyboard, as you remember. The whole crew at SOTUS, I've also learned a lot from working with the social data science people. I continually learn a lot, so this is really fantastic. It's just going to get harder for me, but I'm going to struggle on. You can read it. I'm not sure I can read it out loud. I'm a pretty upbeat person. I think that's genetic, so thanks for that. I found it's not everyone who feels like that, but I'm pretty happy. But more than that, I've also been met with complete trust and support, which is fantastic, and thank you so much. This is just going to get even worse. I'm sorry. Of course, I know. Yeah, just read it. Thank you so much for being awesome. And now this, you see the movement is from big to small. And of course, we need to amend this last part here. Thank you, boys. You're great. And thank you all for coming.